Hi everyone. This video is the continuation of the example of the I-beam, which tries to teach you how you can use Abaqus and Python together to create multiple models. So we left the previous video learning how you can debug the model and how you can change it if you have to. And I would say we've done plenty of tests in the previous videos. There's always going to be errors, no matter how good you are at this process. So expect always a little bit of time testing. The first time I run these models, it would take me maybe a week or two to get them set up properly. But now, because I know what the errors are going to be, I've dealt with them before. Maybe in a day, I can get this running. So the topic of today is going to be the post-processing. And if we have time, I'll teach you how to do the master file. But if the video gets too long, we'll do just the post-processing. If we go back into Abaqus, this is the model that I just ran. And we can go here to job and check the results to make sure everything is okay. So what we've done so far is how you can create a model in Abaqus and how you can run the model in Abaqus. But if you don't post-process the results, that's something that you have to do one model at a time, which basically loses the point of setting up all the models automatically. So what we're going to learn how to do today is how you can then use Python to go to the model that was just ran and extract the data that you need. And then if you want, you can delete the model for economy of space. And therefore, the entire loop of tasks is entirely completed by Python, and you don't have to do anything. And you can have a coffee while this does all the work for you. So let's open Notepad++. And this was the model py that we were playing with in the previous videos. And the way it stands, this code helps you create one model with one set of variables that we have here. But then after it ran the model, it doesn't post-process. So the first thing that I like to do is to take everything that is about the model. So this part here, I'm going to give a little bit of space, and I'm going to hold Shift and click until the end of the script. So this script that's now highlighted here is from creating the model all the way to run the model. And here I'm going to press Tab. And I'll explain to you what I mean by this. And now, with this tab that I just pressed, I can now go into here line 51 and type define def create beam model. Basically, what I just did now is these steps of creating a new model and running it are now going to belong to this function called create beam model. So I can actually minimize it here. If I go back here and I write something without the tab, let's say hello, hello. This is not code, I'll delete it in a second. What Python is now doing is inside this create beam model is all the code that I put the tab in. Now, why is this useful? Imagine that you want to create two models and not one. If you don't have this power, you need to copy paste this entire code 2 times, right? So you can run 2 models. And that doesn't make any sense because once you know the instructions to create one model, you just have to repeat that over and over again. For Python, we always need to put brackets here to tell Python that there's not going to be any variables that we need for this case. And I'm going to show you what happens. Let me delete the hello, hello. Here we go. And now I'm going to show you what happens if I save this. And I'm going to go here on Abaqus. And I'm going to create a new model just for this example. And I'm going to run the script again. So if you guys see, nothing happened. And why nothing happened? And this is important that you understand. Once I told Python how to create a model, I basically telling you, if I ask you to create a model, this is what you have to do. So imagine that I teach you how to make a cup of tea, but then at the end, I don't say anything else. You get the information on how to do a cup of tea, but you don't make a cup of tea. So after I tell Python how to make a model, I need to go at the bottom and tell Python, please create me a model. And now this line, this code 240, is actually going to open this set of instructions that start in line 49. So actually what's going to happen is Python is going to start reading, and from line 46 down, is going to read this stuff, but it's not going to execute it, and only is going to start executing once you get to line 240. So now with line 240, I saved. So let's try again. And here we go. Now it's starting to create the model. I forgot that it's going to run, so I'm going to make sure this crashes so I can continue with the video. Okay, so I opened Abaqus again. What I want to show to you is how you then access the model to retrieve information that you're interested in. So if you go into the folder that the Python model is running, in my case, I think should be folder 8. No, this is the one that I stopped. So here folder 6 was the one that I tested. And in this bunch of files that you see in the folder, there's one that has all the information that you need. And it's this one here that finishes in ODB. ODB stands for Output Database, and it's basically the Abaqus file that contains all the displacements, all the stresses in all the nodes, so you can access them and retrieve them. So the first thing that I'm going to do is open this ODB. So I'm just going to go here into another file so I remember how to do this, and I'm just going to paste it here so you guys can see. Basically, what I'm going to say to Python is save something into a variable called ODB, and this something is going to be with this line here. So session dot open ODB, and here I need where the folder and where the file are. So I'm going to go into the folder test Python 6. I'm just going to copy it here, and I need to make sure this is a string, so it's a piece of text. And then after that, what's the name of the file? It's job1.odb. job1.odb. So I can delete all of this, and here you go. So now this line of code is going to make sure that ODB file is going to be uploaded into a variable called ODB. Now, I could run this here in Notepad++, but as you guys can see, every time I try this out, this is going to run the model, and then I have to wait for the model to complete. So Abaqus actually has a Python console inside the software. So you can actually go here and type something. Let's say print hello. This is Python. It's a console from Python. So I can go and try to open the ODB here, and I get this error, which means I need to put an R here so it opens. And you can search why you need the R here. It's not very important, but you need the R here. So I'm just going to put the R so I don't forget. And now that I have the ODB uploaded here, I'm just going to get a little bit more space. I can start printing the ODB. And you'll see this is going to look very nasty. So this ODB has all sorts of information inside the ODB object. So for example, if I want to see this description, I can type print ODB dot, and let's try like this, trap description, and it gives me the answer DDB object. Okay, so this is the point where probably Python would help you a little bit understanding what's happening here, but it's not essential that you know it. So if I do, for example, ODB print ODB dot, let's go here, name. This is the name of the ODB. Okay, so if you read a little bit, you can start looking for the information you're looking for. So let's say, for example, I want to see the sections inside the model. So I can do print ODB sections, and now it's going to open a set of sections inside this sections object. So this gets complicated very fast, but I could, for example, open this section assembly part 3.1 picked set. So I'm going to try to do it like this. So I'm going to put dot and then paste this, which should not work. Okay, that doesn't work, but that's fine. Once this doesn't work, there is another way to open it, which is putting square brackets around this, and then the quotation marks. There's the dot there that shouldn't be there. Okay, let's try again. So without the dot and with the quotation marks. Okay, so now I opened a new folder, if we say so. So for example, let's see if I want to find the material of this part. I could go here and do dot material, and this will give me material 1. Or let's say I want to find the thickness. I could put dot thickness, and this gives me 8. So when you're doing post-processing, it's quite annoying because you don't know exactly where things are and you need to look for them. And there's no other way. Like if we go back to print ODB into the beginning, this is a massive object with all sorts of information. And it can be a bit annoying to search for exactly what you're looking for. Now, the good thing is once you do it once and you know what you're looking for and you need to do it again, you can just copy paste from a different file. So for example, if I go to this file here, I can copy this statement here, which it says displacements equals to this. We can have a look. So from a previous file, I got that displacements are found in the odb.steps, then the name of the step, and then the frames, and then this I'll show you what this is, dot field output u dot values. So let's try this out. So if I go to print odb, somewhere there should be something called steps, which is here. So this one I can do print odb dot steps, and now I'm accessing that step, and now it's telling me that inside steps there's only one object called step 1. So fine, if I want to access this odb object, I need to do now with brackets dash step 1, and now let's see what's inside. And now it's telling me inside step 1 there's acoustic mass, description, there's all sorts of things, but I know that the next thing I need to do is frames. So I can go and say odb steps dot frames. So now once I open frames, there's all sorts of odb frame object. And what this is, I can show you what this is in a second. So if I go here and I open the odb in Abaqus, it's here in folder number 6, and I want to open the odb. So if I open this here, and let's look into the results very quickly. So these are the results. So you can see that this model ran 100 different steps. So what the frames are is each one of these steps is saved in a different frame. So if you want frame 42, where the step is 0.42, you can just type 42 and you'll get that one. But let's get the last one so we can get the number 100. So I can go here and I say, if you count this one, so I can show you another thing, which is do the length of this. So you can see the length of this is 101. So it gives you the initial step as well. Now that we know what's inside this frames object, we could, for example, select what's going to happen in position 100. Oh, I forgot to remove the length. So let's remove this length to print. So now what we're basically doing is access the last object. So one thing you need to remember in Python is the first item is 0. So this is 0 here, not 1, which means the last one will be 100. And now inside the one in 100, you can see there's all sorts of information as well. And the next one we're going to need is the field outputs. So if I go now print this and dot field outputs, I'm writing it exactly as it says here, and let's see what this does. So now here we have all the field outputs that were asked from Abaqus to be printed. So most of them we don't need, but for example we have S, which is for the stresses, which is the one that is active. But if you go here on U, that's the displacement, so we can also access that. We can go UR, which is the rotations, and I think CF is the applied force, which you can see it's just there. So you can get all the information that you see in Abaqus, you can get in the ODB file. Now, what else is there? So we're definitely going to go into U to get the displacement. So after that, I'm going to try, let's try .u, so you see it won't work, but that's fine. Once this doesn't work, try with the brackets and then quotations around, but without the dot. And now we are inside this U component, and it says we have component U1, U2, U3, but now the one we need is this values one, and now it's going to go crazy because we have lots and lots of nodes. Once you press values, this is all the nodes that you have in your structure. So if I want, let's say, node number 1, I can get position 0, and this is the displacement on node number 1. That's U1, that's U2, and that's U3. So for me to access that, I need to do dot data, which is here. And if I do dot data, that's the ones. And now if I want U1, I want the one in position 0. So it took me a while to go through this ODB and unpack all this craziness. But once you do this once, you know that this piece of code measures the displacements on the last step, or on step 100. In node number 1, and this is U1. Now, one of the things that is useful in Abaqus is when you change the mesh size, the nodes could end up in different positions that you expect. But Abaqus does something that is very useful, which is if you go and try to find the labels, so I'm going to go here, show node labels, and those are the labels. If you zoom in, you see node number 1, node number 5, node number 6, and 3. And if you check on the other side, there's going to be node number 4. Abaqus always names the edges and the vertices of your structure first. So no matter what the mesh size is, node number 1 will always be that center node. And if you want to know what is the other nodes on the other side of the structure, there will always be 9, 10, and 17, no matter what happens with the mesh here. Obviously, these 505, 547, these will be dependent on the mesh, while these ones in the edges will not. So if you want to know what is the displacement here at node number 1, the only thing you need to do is exactly what I've done here. So that will be U1, but if I want U2, I can just change this data from 0. Let's delete it so you can see it again. So 0 gives me this number, 1 gives me this number, and then 2 will give me this number. Okay, so I'm going to put here 1. That will give me U2. So if I go here and try to measure U2 in that particular point, you can see that the answer, we can go and check here with a little I for nodes. If we click that node over there and we press enter, we can see the displacement is 9.96068, which is exactly what this piece of code gives you. So now that I know how to get the displacement in the center, what I'm going to do is transfer that back. I knew that more or less already. Like if you can see, I copied this from another file. I knew I had to go through steps, frames, field output, U, values. So I know this is how I get displacement. So I'm just going to call this central displacement or central disp equals this. And I'm going to get rid of this. So I have a function that creates the beam. And now I can create another function, which is called, let's say, post-processing, which will do exactly this. Say that the ODB is in this place. I just need to be careful here with this 6, but I'll fix this in a second. And I know the central disp is this one for the last step. So I'm just going to go, for example, and print the central disp for now. So we can see if it's working. And again, similar to before, here I'm just telling the software how to do the post-processing. So I need to call it here. So I first create the beam and then I do the post-processing. So the only thing I'm going to change here is this 6. So I know this 6 is something that is created all the way here on the top when I create the folders. So this has a name called folder name. So I'm just going to go all the way down and say instead of the 6, I'm going to replace this with plus and then folder name and then this. Is this correct? Doesn't seem like it. Here we go. And then another plus. So this should work now. Obviously, if something doesn't work, we'll see it once we run it. Now, another thing that is interesting is what happens if, for some reason, we don't get 100 steps. So one thing that we can do is find this piece of code here, and I'll explain to you what this does. So this is the ODB, it's in this folder, and then the number of steps is the length of the frames inside step 1 ODB. So it's something that I showed you here, how to get this 101 here. So actually, let's try this with 101 to see if this works. No, it's out of range. Okay. So now that I know this, inside here, the 100 is going to be number of steps minus 1. So this should then give me the central displacement in the last step once I run this model. So I'm just going to save it now. And remember, now the beam model is here, post-processing is here, and now let's give it a go. So if I go back here on my Abaqus, I'm going to run the script. This is going to take a while, so I'll pause the video. So desktop, test Python, and model.py. Let's see if this runs. So far it runs, which means there's no errors, which is expected because we're still trying to run this part. So we're still in line 247 running the creation of the job. And once this is done, we're going to go to line 239 when this part gets active. So we might get an error here, I'm not sure, but we only are going to find out once the model completes. So I'm just going to pause and I'll be right back. Okay, so I got my first error, and this is where having a little bit of Python knowledge helps. It's saying that the error is you cannot add a string to an integer. And basically what it's saying is this folder name here, it's a number, so it's not a text. So what we need to do is change this folder name to str fold name. So this should change the integer to a string. So now let's run it again and see if I don't get any more errors. Here we go. Okay, so I'm getting another error which has to do with not being able to find this file inside folder number 10. So I can go and try to see if I can find it. So the file is there. So this is a problem that is very annoying with Python, but what I'm going to do is solve it the only way I know how to solve, which is by replacing all these bars to go into the other direction. And please don't ask me why there is just the way it is. So now this should be able to work. So I'm going to save and run again. Okay, now we wait. So we don't have any more errors. As you can see here in this region of Abaqus, we got the creation of the elements, then we got the analysis to start, job 1 was completed successfully, and then we get this message, and then at the end we printed the maximum displacement. So this is one example of post-processing. It's a very simple example. You can do all sorts of shenanigans with this. But I think for the time being, this is not too bad. Or actually, let's do another interesting thing, which is how to do a plot. So if I'm going to go and get the plotting code, so I'm just going to find that somewhere, and I'll teach you how this is done. Okay, so I finally found something where you can plot. So I'm just going to copy this here. And here we go. So basically what this code does, and again, this is not important that you don't know exactly what this does. So it plots, let's call it an X and Y. So let's change this to X and change this to Y. So it plots several points, and then this is just color red, and then with the label U2, which actually is the same in this case. This probably will do the legend. And again, this is something you can check online. It's not important. I just copied this from another page anyway. And then the displacement's going to go into the X label, and then Y label is the applied loading in kilonewtons, and then the title is force displacement curve. So that's basically what we're going to do in this case, is a force displacement curve. And here this just saves the plot in a figure called maxdisplacement.png. So one of the first things I'm going to do is get the library PLT into the software. So I'm going to go here and do import matplotlib. So it's the library that does plots as PLT. Actually, it's matplotlib.pyplots. I actually don't know this by heart, so let's go online. So if you go here, matplotlib, Python, maybe this one. Here we go. Import matplotlib.pyplot as PLT. So this is even hard to say. So I'm just going to copy this. See, I wasn't wrong, but okay. So now I have the library pyplot as PLT, and this library has all these functions in it. So now the only thing I need to do is to get X and Y. So if I want to do a force displacement curve, I need in X to get the displacements, and I need in Y to get the forces. So the first thing I'm going to do here, now that I know the number of steps is a variable, I can go here and say for I in number of steps, or actually for range in number of steps. So basically I is going to go from 0 all the way to the number of steps. So I can show you this here in Abaqus very quickly. So if I do for I in range 10, let's say, and if I say print I, let's see if this works. Okay, there's the indentation problem. So for I in range 10, now I'm going to give 4 spaces and do print I. it prints 0, 1, 2, 3, 4, 5 until 9. So basically this is going to find all the frames until it gets to the end. So now that I do this, I can go and take the central displacement, and instead of getting it in the last frame, which is number of steps minus 1, I want it in frames I. So it will get you the first one, the second one, the third, so on and so on. And I can print this for you just so you can see what it does once we run it. Now, another thing that I want to do is put this somewhere so then I can plot. So I'm going to create here a list, an empty list called displacements. And after I find the central displacement, I'm going to go to this list called displacements and append the number that I'm calling central displacement. Okay, I hope this is making some sense. So basically this is going to be an empty list, and once this starts running, this is going to be the number that we're going to fetch from Abaqus, and then this command here puts that number into that list. Okay, then we can also print the displacements list so you can see. Okay, now the only thing I need to do is the same, but now for the loads. So if I want to do a force displacement curve, I need forces and I need displacement. So I'm going to go forces is empty, and then I want applied force to be something, and this I need to change, but I want then in the list called forces, I want the applied force to be appended. And now let's try to figure out how we can get this applied force. So if you remember correctly, and if you don't, that's fine because I don't either, the load that we apply is minus 5,000. So once we get to visualization and we check this CF, this is where the loads are applied, you can see that where it's red, it's 5,000. It's actually positive in this case. But how can I find this number? And we're in the final step. That's another thing that is important. Since we are on the final step, the load that we have, the load that we applied is going to be the same as it's here. So let's try to figure out how to get to that force. So I need to get if the ODB is still around. So is this still working? Yes. So if I print the ODB, this is still around. So now let's try similar to before. Probably it's going to be steps, then step 1, then frames, and we can get the frames 100 for now, the last one. And then we're going to go field outputs. And now this is the part that we probably need to start having a look. Did I make a mistake? Yes, I did. So I forgot to put a quotation there. So does this print now? Yes. And now I'm going to go into the CF, so field outputs, and then CF. And now inside I have all these objects. So let's try the values. So dot values. And again, lots and lots and lots of values. And now it is interesting because it still has one object per node. So let's see randomly the node 34. This should be 0, 0, 0. So it's basically saying that on node 33, there's no loads being applied. But we know that our load is now in node number 2. If it's in node number 2, if I put here 1, here's my 5,000 there. So now once that is done, I do data. And now I do position number 1. And that's my minus 5,000. So the applied load is going to be this. And because it's negative, what I'm going to do is multiply it by minus 1 at the end. So then it becomes positive, and this will look very nice. Now the displacement, is it positive or negative actually? Let's have a look. So if I copy this here, and I have a look, so this is negative. And let me see in position 100. That's also negative. So I'm going to multiply by minus 1 as well, just to look prettier at the end. So times minus 1. Okay, so this looks good. We print now the applied force, just for you guys to see. And then we can print the forces as well. Actually, let's not do this because it gets too confusing. Just going to delete this. And we'll see. Once we have our X and Y, we're just going to put it here. So in X, I want the displacements. And in Y, I want the forces. So hopefully this will work. If not, there's no problem. We can check once we start getting errors. So now it's a little bit more advanced. Not only we're going to get the central displacement, but we're going to do it on all the frames. And there's an error here. We need to change this to I. We're going to do in all the frames, and then we're going to plot. And let's see how this works. So save, and now let's run and hope for the best. Okay, let's check if this ran. So if we go back here, here's all the data that we asked to print. So it's a lot of mess here. So what did we ask to print again? So first the central displacement and then the list. So as you can see, let's see how big this is. Is there a way to go to the beginning? So throughout the process, it starts with just one number, which is 0, and then it adds the next number to it. So as you can see, the list keeps growing and growing and growing for at each frame that it's being read by Python. And once you get to the end, you have 100 different displacements. You also have 100 different loads. So if you go now into the folder, the last one, which should be this number 12, you're going to find here the maximum displacement.png, which hopefully gives you a beautiful little curve with the force displacement, which is elastic. Yeah, makes sense. Okay, this is looking good. So this is it for today. We learned how to do a bit of post-processing. In future videos with different examples, I'll show you other tricks that you can learn how to do. But I think for now, this is pretty decent. We learned how to retrieve data, but also how to plot it in a figure. In the next video, I'm going to show you how you can create, let's say, 10 models in a row, but in theory, you could do 10,000 without having to touch anything, which was what I promised to do in the beginning. So with one more video until the end of this little series, and then we'll see where we go after that. So thank you for watching and have a nice day.